Okay, so good morning everyone. So today we're going to continue our discussion of fiction. Okay, so we're going to start with a very nice problem here. Okay, so in this problem we have here a wheel. Okay, let me. So we have this wheel over here, okay? This is the center, okay? It's rotating about this center. So this wheel is rotating about this point, okay? So there is like some pin at the center here. This is point O. The radius of this wheel is R, okay? And now there is a moment, M naught, applied on this wheel, okay? So since the center point here, point O is pinned, so point O here is pinned. What will happen if you apply this moment M naught on this wheel? It will just rotate, right? It will rotate. So to prevent it from rotating, we have some brake system, okay? So we have brake system here. The brake system is simply having, let's draw it in this purple color. We have a like kind of a rod here. This okay, and it's pinned here. Okay. So if you want to break this wheel, okay, if you want this wheel to rotate, you just move this up, it's going to rotate, you know, smoothly, nothing is preventing it, okay? If you push this down, okay, pull this down here, what will happen is it will interact here with this wheel to prevent it from rotating, okay? So it can actually, if the wheel is rotating, it can prevent it, you know, or stop it from rotating. Or even if, you know, it's not rotating yet and you just apply this and there is this moment, you need to apply some force P, okay, to prevent it from rotating. If this force P is so small, it will not be able to prevent it from rotating, okay? So in this problem here, we are required to find how much is the minimum force P, okay, to prevent this from rotating. So this distance, we're given those distances here. This distance is A, and the distance from the contact of this rod to the hinge here is B, and this height is C. Okay? So here, this is not a solved example in the book, okay? This is a problem actually at the end of the chapter. So we're required to find how much is the force P that we should pull down on this wheel, okay, at the end here, to prevent this wheel from rotating under this moment, M naught, okay? So right now, the wheel is in equilibrium, okay? Even with this moment M naught, it is in equilibrium because of the effect of the force P, okay? It's preventing it from rotating. So we want to find the force P. So how to do this? Yeah, now you should be an expert. What's the first step?
Draw the
free body diagram. How many objects do we have that I have to draw the free body diagram for? Two. So let's draw the free body diagram of each of those objects, okay? So I'm just going to copy here. So the first step is the free body diagrams, okay? I'm just going to copy this and paste it here twice. And again here. So here I'm going to have the two parts, just separating them here. So those are the two parts that we have, okay? We're drawing the free body diagram. So what is the free body diagram of each of them? I removed, like, there was this wheel, it's interacting with what? With this pin, right? So there are two forces here. let's call it point O, so O Y and O X. And then this wheel was interacting with this rod at this point, right? So what do we have here? If it's a smooth surface, then we have N, okay? You're pulling here with P, so this will be converted to a normal force here, pulling on the on the wheel here, okay? And then, if you have this moment N node, it wants to rotate this wheel in this direction. So the direction of impending motion, this point wants to move in this direction. So there will be frictional force preventing it from moving, right? So this is the direction. This is the direction of impending motion. Let me draw it in another color. This is direction of impending motion. That means that there is a frictional force here, okay, perpendicular to that normal force. It's a frictional force, and now we're on the verge of equilibrium. Why? Because we're talking about the minimum force P, okay, to prevent the rotation. So it's we're on the verge of equilibrium here. So this F is just Fs, which is mu s n. Okay? So that's the free body. Those are the forces acting on this wheel. Now, what about this rod? What are the forces here? Apply them. First thing, those two objects were in contact at this point, right? We know for every action, there is a reaction here. Okay? So if we have N here, we're going to have an equal and opposite force, N. And here we're going to have an equal and opposite frictional force, which is mu Sn. And then at the hinge, at point C, there will be two forces, Cy and Cx. Okay? We would like to find how much is the force P. Okay? So as you see here, what are the unknowns? We have P, 1, N, 2, Cx, Cy. So those are 4 unknowns. How many equations of equilibrium do you have? 3. So those are not sufficient. So let's start with the equilibrium of this wheel. Okay? How many unknowns do we have here? M node is given, okay? R is the radius that's given, okay? So we only have N, okay? N is the only unknown here. So we can simply start studying the equilibrium of the wheel. So from the equilibrium of the wheel, we have sigma fx equal to 0. Sorry, here we have 3 unknowns. Sorry, I said 1, N. No, you have N, Ox, and Oy. Those are 3, okay? Ox and Oy are not known as well. We're interested in finding N, okay? We are not interested in finding Ox and Oy. How to eliminate Ox and Oy from our equations of equilibrium? What equation of equilibrium would you use to eliminate Ox and Oy? Moment about point O. Okay?
Then also the force, the friction force, which is, we don't know, so we have 4 unknowns.
No, this is N, and this is mu Sn. So it depends on the same N. Okay, there are no, it's not 2 separate unknowns. So now I'm just going to take the summation of the moments about point O equal to 0. What are the moments that we have? What's the moment of Ox? 0. What's the moment of Oy? 0. What's the moment of N? 0. What's the moment of the frictional force?
Negative
Us N multiplied by its distance to point O, which is the radius. Is it rotating clockwise or counterclockwise?
Clockwise, negative.
It's clockwise, so it's negative. So negative mu s n multiplied by the distance r. What else do you have?
The moment M.
The moment m naught. Okay. Is it positive or negative? Positive. So m naught multiplied by r, right?
Yeah.
No.
No, it's just a moment.
Just m naught. Okay. The moment is the same. This is a couple moment. It's the same about any point. Okay. Not multiplied by any distance. So that is equal to 0. So from this equation, I can find n. So how much would n be? M naught divided by mu s r. The moment divided by the coefficient of static friction. I always forget to use my phone. The coefficient of mu s, the coefficient of static friction divided by the radius r. Okay. So as you see here, it's m naught divided by r. Okay. Mu. So this force mu s. Okay. Is equal to m naught divided by r. The horizontal force is equal to m naught divided by r. Okay. We're gonna use this just in a few moments. Okay. So here, mu s, the horizontal force, mu s n, which is the frictional force, is equal to m naught divided by r. Okay. I'm going to use this not in this problem, but later on. Okay. So n is equal to mu s, the m naught divided by mu s r. So now I know how much is n. So I'm going to start writing the equilibrium of the rod then. From the equilibrium of the brake system, now I know n. N is m naught divided by mu s r. Okay? I would like to find p. Now those are not unknown, right? I know them in terms of m naught, mu s, and r. I would like to find p. What are the other unknowns that I don't have here?
Cx and
Cx and cy. I was not asked to find Cx and cy. I want to eliminate them. So how to eliminate them? Take moment about point C. Okay? So let's take the summation of the moments about point C. Let's just copy this here so you have this available to you. Paste. So take the summation of the moments about point C equal to 0. So what do we have here? What's the moment of Cx? What's the moment of Cy? 0. What's the moment of the force P?
It's positive.
It's counterclockwise, so it's positive. P multiplied by A. It's distance A. What else do you have? The force N, right? It's negative. It's rotating in a clockwise direction, so we have N, okay, which is m naught divided by mu s r multiplied by its distance to point C. What is that? B. What else do you have? This force, mu s n. What's the moment of this force about point C? No. There is this, you know.
Yeah.
So it's this force multiplied by this distance C. Okay? Is it positive or negative?
Positive.
It's negative. It's rotating clockwise. So we have negative here. Mu s n, which is m naught divided by mu s r. Right? The mu s cancels with the mu s, and then you multiply this by the distance c, that is equal to 0. So here we have P A minus m naught divided by r multiplied by P divided by mu s plus C. Right? Just two common factors here. Negative m naught divided by r, so I have P divided by mu s, m node divided by r, I only have c. Right? So now, moving this to the right-hand side of the equation, so we have m node divided by r, p divided by mu s plus c. So p is how much then? M node divided by ar, p divided by mu s plus c. That's the minimum force required to stop this wheel or prevent this wheel from rotating. It's not rotating, okay, to stop it. We want to prevent it from rotating. That's the minimum force. If P is less than this, then it's not going to be able to prevent it from rotating. It will rotate, okay? If it's higher, so definitely it's stopping it as well. But this is the minimum force required to stop it from rotating. Any question here? Okay. So now, as you see here, when we had this circular shape with some moment m node, okay, this gets converted to a horizontal force here, okay, frictional force or a horizontal force, okay, of m node divided by r to be in equilibrium, okay, m node this moment divided by r, okay. I'm just going to use this now in our new discussion, okay? We have a new topic now in the friction. So, but we're going to use this now. So we're going to apply what we learned in friction on square threaded screws, okay? So application of friction forces on square threaded screws. So I'm not so good in drawing those things, but I'm going to try my best here. What's a screw? You have something like this, okay? Square threaded, you have some threads here, okay? On this screw. And what's the point of a screw? How do you use a screw? Simply, you apply a moment here, M, okay? To make this screw move up or down. Right? That's the purpose of the screw, right? You just rotate it, right? And then it moves up or down. So you transfer the moment, okay, to a vertical, okay, longitudinal motion, okay? So usually, so here this is the shaft of the screw, and here those are the threads. We're talking here about specific case of square threads. So the threads here has the shape of square, okay? There is V threads, okay? But no, our discussion here is on square threaded screws, okay? So this shaft here, usually there is like a guide here, and then there is friction in between. Okay, you want to move this along the sides here, okay? Applying the moment, it moves down along the sides here, like this. There is some sides here. And then you apply this moment, so it moves up or down. Okay? So now, how those threads look like? Okay? So the threads are the point of contact between this part and the screw itself. Okay? So those are the threads. Okay? So thread goes in a helical shape. Okay? So now we want to define some distances here. The vertical distance here for this helical to have one loop, okay, we're going to call this L, standing for the lead, okay? So that's the vertical distance of one loop, okay, in the threads. So what we want to do now, let's say the average radius here of the shaft of the thread is R, okay? So what we're going to do here is we're going to unfold one loop here. Just going to, you have something like this, you're just going to, unfold it to a straight line, okay? So unfolded or unraveled here. This is the unfolded loop. Just one, okay? So as you see, this loop goes up, okay? So when folding unfolding one loop here, there is an angle at which this line goes up, okay? That's the angle theta, okay? So how much is, so the theta here is the angle of the thread, okay? How it goes up. So how much is this vertical distance? L. It goes up in one loop, it goes up a distance L. And how much is this distance? One thread was going around the circumference here.
Maybe 2R.
2 by?
2 pi r, right? The circumference of one loop, okay? So here you have 2 pi r, okay? So r is the average or the mean radius of the shaft here, okay? So this is 90 degrees, okay? So now, how much is that angle theta? The tan theta is what? L divided by 2 pi r, right? So if you know L, the lead, the radius of the shaft, you can find this angle, okay, the angle of the threads. It's tan inverse L divided by 2 pi r. So as you see here, this angle theta is simply a property of this shaft or this screw, right? So it depends on, once you have a screw, okay, the angle theta is known, just knowing the length here, okay, the lead and the radius of the screw, okay? You can, know the angle theta. It's not changing, okay? So this is theta now, okay? So as we said here, what's the purpose of this screw, okay? The only purpose of this screw in life, okay, is you apply a moment to move it up or down, right? So now, applying the clockwise moment moves the screw up, okay? And applying a counter clockwise moment moves the screw down, okay? And when no moment is applied, we just need that this screw stay in place, okay? Doesn't move, okay? What would cause it to move? The weight, okay? The weight of it, okay? The weight of the screw. So need to be in equilibrium under the effect of the weight. In this case, we call it self-locking. So what we're going to try to study here is the two cases, okay? The first two cases. When you apply clockwise rotation to move the screw up, or applying counterclockwise moment, okay, to move the screw down, okay? So, yes?
When you say clockwise, which end of the screw are you looking at?
Okay, so this, okay, we're moving it up, we're getting it clockwise, so it moves up,
You're looking at the head of the
yeah,
screw.
the head, yeah.
So you got left-handed threads then, you get reversed from normal threads, right?
Yeah, yeah, here it's going to be the opposite. Okay? So now, the question that we have here, okay? You know, you have some screw, okay? Someone before you was so strong, he tightened it so hard, right? You want to unscrew it, you want this to start moving, okay? You apply a moment, you get the, you know, your wrench, you start, you know, rotating to apply a moment, but it's not rotating, right? Why? Because it was tightened so hard, okay? So now we want to see, okay, how much moment is required, okay, to start this motion, okay? How much is the moment required to start the rotation, okay? Whether to move it up or down, how much is the moment? We want to find this formula, okay? So how much moment is required to move? So what we're going to do here is first we're going to study the first motion to move the screw up, okay? To move the screw up, okay? So now we have upward impending motion, okay? We have the screw here. Let's draw a 2D vision of it, okay? And there is, we want to move it up along this, you know, other part here, okay? So we're applying a moment, M, clockwise moment, to move it up, okay? So here, the contact between the two here, we have this distance H, okay? The contact between the two. And here we have this average R, okay? So what we're going to do here to study this, we're going to unravel the threads along this distance R, okay? Unravel the threading along the distance H, the contact distance between the two parts, okay? So now the threads, this is the threads, okay? All the threads unraveled, okay? So what's the angle here? Theta. The angle of the threads, okay? It's a property of this screw itself, okay? Depending on the lead and the radius of the screw, okay? Now you apply a moment M, right? You are applying a moment M. So this moment M will get translated to a horizontal force of M divided by R, okay? How did I get this? From the example that we just solved. Do you remember this? The horizontal force is M divided by R from equilibrium, right? So now I have this horizontal force M divided by R, okay, that wants to move this thread, okay, up along this distance H, Okay, wants to move this up. So also we have the weight of the screw itself, okay, or any force applied on the screw, okay, any vertical force applied on the screw plus its weight, W. Now this wants to move up, okay, so here we have the direction of impending motion, okay, it's in this direction, this is the direction of impending motion. So there is a normal force here due to the contact between the two surfaces, the threads and the other red part here, okay? And there is a frictional force here, F. We're asking about how much is the moment required to start the motion. So F is how much? No, not 0. It's the static frictional force. It's mu S N, right? Because you're on the verge of equilibrium, right? You're going to start the motion, okay? You need M, the moment M, to start the rotation, okay? So mu S N. So if this angle is theta, so this angle here from trigonometry, this is theta as well, right? Now we have those two forces, N and F. Okay? We have a resultant force of them. So what's the resultant force of those two forces, N and F? Let's call it R. Okay? How much is this resultant force? N squared, square root N squared plus F squared, right? What's the angle here? What's this angle here?
90 minus.
No. This angle here.
Arctangent of USN.
Hmm?
The arctangent of USN divided by N.
Raise your voice.
Arctangent of mu SN divided by N.
It's, yeah, so this angle is phi s. The coefficient, you remember we said the coefficient of friction, you can represent the coefficient of friction. You have mu s, okay, which is tan inverse, okay, the phi s, right? Sorry, tan phi s, right? So this angle here, phi s, is just tan inverse mu s. Do you remember this? I'm just going to go up to show it to you. What I'm talking about here.
It's just canceled.
Yeah, here it is. This angle is phi s, okay? The resultant force here. This angle with the normal force is just phi s, okay? And as you see here, phi s, okay, is tan inverse mu s, okay? Because it's tan inverse fs divided by m, okay? So now this angle is phi s, okay? So now we have this resultant force R. It was the resultant of those two forces. Now I would like to analyze it into two components in the y and x direction. Why am I interested in resolving it into two components in the x and y direction to be in the same direction here so that I can apply my equations of theory, okay? In the x and the y direction. So that's what I'm going to do here. I'm just going to resolve this R into two components. How much is this angle from R to the vertical direction? Phi s plus theta, right? That means that this component is R multiplied by cosine the angle, which is how much?
Yes.
phi s plus theta. What about the horizontal component? R sine phi s plus theta. Okay? Now I'm just going to go ahead and apply the equations of equilibrium. So let's start with the horizontal direction. What are the forces in the x direction? The summation of the forces in the x direction is equal to 0. What are the forces in the x direction?
Sine ds plus theta.
M divided by r. This is the force that wants to move the object, the sliding force. Okay?
Negative r sine theta.
Negative r
Five.
sine phi s
Sine.
plus theta. Anything else? Any horizontal force? Other horizontal force? That's it. So that's equal to 0. So that's equation 1. Okay? So m divided by r, okay, we're interested in finding m. So m is function of r, but we don't know how much is r. Okay? We don't want this equation to be function of r. Okay? So let's use the second equation of equilibrium, the summation of the forces in the y direction. What are the forces in the y direction?
Negative value.
Negative w
Plus r cosine ds.
plus r cosine phi s plus theta. Anything else? Anything else? No. Those are the vertical forces. Okay? So now what I'm going to do, okay, is I'm going to multiply this equation. Multiply, so by tan phi s plus theta. So what would it become? Negative w multiplied by tan phi s plus theta plus r tan multiplied by cosine
The sine, it's going to be sine.
sine phi s plus theta. That's equation 2. Now, what I'm going to do is I'm going to add the two equations. So we have m divided by r minus this plus this. What happens? They cancel.
Cancel out.
Right? And then plus this term, it's a negative. So we had here negative w tan phi s plus theta equal to 0. So therefore, the required moment, okay, is equal to w r tan phi s plus theta. That's the required moment to start the rotation. Okay? It's function of what? It's function of this force, W. The normal force, okay? On the screw. Okay? It's function of the radius of the screw. It's function of the angle of the screw. It's function of the frictional force between the screw and the other part. Okay? So now let's go back, just a reminder of, do you remember I told you, some strong guy before you tightened the screw so strong, okay? So you need a larger moment, right? So in this equation, where does this part comes in? That some strong guy tightened it so hard before you.
PS.
No, phi s is the coefficient of friction. It has nothing to do with this guy who tightened it before you, right?
The R.
R is the radius of the screw. It remains constant. It has nothing to do with this guy.
So at the moment,
No, we're talking here that the moment has to be large, right? So definitely this guy before you has nothing to do with theta, right? when he screwed the, tightened it so hard, he didn't change the angle of the screw, right? The lead, the radius didn't change. He didn't change the coefficient of friction. Coefficient of friction is a material property. It has nothing to do with this guy, okay? He didn't change R, the radius. He changed W. When he screwed it, when he tightened it so high, so strong, okay? He moved it to the, limit, okay? Increasing this normal force, this W, the weight. It's not only the weight, he applied a vertical force on the screw, okay? He moved it to the end, so the screw is under tension because of this guy, because he screwed it to the end, so it's under tension. So he actually increased the force W. That's why now you need a larger moment to unscrew it, okay? So now, this formula, okay, I will give you this formula on the test, okay? You don't have to memorize it, okay? But you really need to understand what each term here means, okay? So now, we answered the question, how much moment is required to move the screw up, okay? What do you think now? If I ask you, how much is the moment required to move the screw down? Is it the same?
Negative.
Is it the same moment? The same magnitude? Let's see, okay? Let's try to answer this question now and see. Here we're going to have two cases, okay? So the first case, if the angle theta is less than PS. So PS, the angle PS, is larger than the angle theta, okay? So here, again, we have this, we're just going to do the same here. We have this unfolded, okay? So this was the unfolded threads. So here we have the unfolded threads. That is the force W, okay? And now, the only thing that changed here now is the direction of M divided by R. It became the opposite direction. And now the direction of impending motion, you want to move this down. Direction of impending motion. And then again here we have this force N. If this angle is theta, so this angle here is theta, okay? What's the direction of impending motion? This wants to move down, right? So the frictional force is this direction, which is mu s n, right? And now you have the resultant force R. So the resultant force R, okay, is here. Why is it here, not here? Because we're saying here, this is the case where this angle PS, okay, is larger than theta, okay? So now this angle here is phi s. It's larger than the angle theta, okay? So now I want to find the components of R, the vertical and the horizontal components of the resultant force R. So how much is this angle now? Between the vertical and R. ES minus theta. Okay? So this angle here is phi s minus theta. So that means that the vertical component is R multiplied by cosine the angle, right?
Yeah.
So cosine phi s minus theta. And the horizontal component is R sine phi s minus theta. Now applying the equations of equilibrium, the summation of the forces in the x direction equal to 0. What do you have?
Negative M over
negative m over r
Plus R.
plus r sine Ps minus theta equal to 0. That's equation 1. Okay? And then we have the summation of the forces in the y direction equal to 0. What do we have? Negative W plus R cosine Ps minus theta. That's equation 2. We're going to do exactly as we did, okay, for the upward motion. Okay? So we're going to have here M is going to be WR, but it's tan Ps minus theta. Okay? So here we got this formula. This formula is for upward impending motion. Okay? Here, this is the formula for downward impending motion with phi s larger than theta. Okay? If theta is larger than phi s, we're going to do the same. I'm not going to draw it, but you can do it yourself if you want. So similarly, you're going to find that m is going to be WR tan theta minus phi s instead. Okay? So you have three formulas. But here it's less. Okay? One formula for the upward motion and two formulas for the downward motion. Okay? That gives you the magnitude of the moment required to start the rotation of that screw. Yes?
So it's one formula upward regardless of which direction the threads have been actually threaded. Correct? Yeah.
Yes.
It's just for the upward motion regardless.
Okay? So now let's solve a very quick, short example here. So this is example 8.7. So in example 8.7, okay, we have the turn buckle, okay, that has square thread with a mean radius of 5 millimeters and a lead of 2 millimeters. What can you get from this information? You can get the angle theta of the threads. Okay? If the coefficient of static friction between the screw and the turnbuckle is mu s equal to 0.25, we're required to find the moment m that must be applied to draw the end screws closer together. So what's this? I'm just gonna, oops, copy this here. So this is the problem that we're talking about here. Just gonna make this smaller. So that's what we have here, okay? We have this stem buckle here with those two screws, okay? And we want to rotate this, okay? So these two parts move closer to each other, okay? There is a tensile force here, okay? It's not shown here, so we're gonna show this other figure, okay? And I have to just make this smaller. Okay, so there was a tensile force here. The guy before you, okay, the strong guy, okay, there was, they tightened this so hard, so there was a tensile force here of 2 kilonewtons, okay? Now we want to start rotating this so that those moves toward each other, okay? Actually, we want to increase this tensile force, okay? We want to rotate this so that those two parts move closer to each other, okay? So now, if those two parts, so this is the screws here, this one and this one, we want those to move towards each other. So this is an upward motion, okay? We move up, this one will move up, okay? And this one will move up, okay? We just want to find how much is the moment required to apply here so those two parts move up, okay? Look, this part will move up along this part here. Moves up, okay? And this one will move up regarding to this part. You rotate like this, it moves up. You rotate like this one moves up, okay? They're moving closer to each other, okay? So now, how to solve this problem? It's a one-step problem. How much is the required moment? You just find the formula. Which formula we're going to use? The upward motion. W R tan phi s plus theta. Right? W, the required moment, is M, which is WR tan phi s plus theta. You agree? Everyone is all right with this? No, this is wrong. Okay?
Yeah, because the screw's going down.
Because you have two screws. The moment that you're going to apply is going to be divided by two screws, right? You're moving two parts here, okay? So you actually require twice this moment to move both parts, okay? The formula that we had was required to start the motion for just one screw. Here we have two screws that need to start moving, okay? So we need 2 multiplied by WR. So here, because we have two screws, we have 2 screws to move. So now, how much is W. We just want to find those parameters in the equation. We want to find M. Do we know how much is W? 2 kilonewtons. So W is 2 kilonewtons. Okay, that's W. How much is R? It was given 5 millimeters, right? 5 millimeters. We need phi s. How much is phi s? Do we have phi s?
Inverse tangent of
Yeah. Tan inverse 0.25. Theta. Do you have theta?
We can find
Theta, the angle of the threads. The lead and 2 pi r here. That's the angle theta. So theta is tan inverse L divided by 2 pi r. Right?
it's gonna be
Tan inverse
2.
L divided by 2 pi r. So it's tan inverse. How much is the lead? 2 millimeters. Should I change this to meters? No, as long as you keep the radius in millimeters as well. So it's consistent units. So theta is going to be equal to 3.64. And phi s is 14.04 degrees. Okay? Just put the numbers in the equation. So M is 2 multiplied by W, which is 2 kilonewtons, multiplied by R, which is 5 millimeters, okay? Multiplied by phi s, sorry, tan, multiplied by tan, phi s, which is 14.04, plus theta, which is 3.64. So plugging the numbers here, we're going to get the moment is going to be equal to 6.3747. What's the units?
Newton by
Kilonewtons,
by millimeter.
millimeters. Okay? So I can change this from kilonewtons or from kilonewtons millimeter to newtons meter. How can I change this from kilonewtons millimeter to newtons meter?
Divided by 1000.
Changing from kilonewtons to newtons.
1000.
I have to multiply by 1000.
Oh.
And changing from millimeters to meter.
Divide 100.
Divide by 1000.
it's not complicated.
So it's the same number, but it's in Newton meter as well. Okay. Just multiply by 1000 and divide by 1000. So you're doing nothing. Okay. So this is the answer. This is the required moment to start the motion. Okay. Any question here? Okay, great. So let's move forward, okay, to another topic, okay, another application of the friction forces, okay? So we're going to study frictional forces on flat belts. Okay? So now, let's say you have some circular part like this, and there is a belt. Let's draw the belt in another color. You have this belt. Going like this, okay? And there is a tensile force in it, okay? T. You remember earlier we said if you have a smooth surface, the force T has to be constant, right? But now we're talking about having some friction here, okay? So if you have some friction here, okay, this force T will not remain constant, okay? The frictional force will make it change, okay? So we have some force T1 and some force T2, okay? So what is the relationship? You apply the force, let's say T2, okay, to pull the cable or the belt, okay? You want this to move, but the frictional force is preventing it from moving. T2 is going to be less. What's the relationship between T2 and T1? That's what we want to find, okay? What is the relationship between T2 and T1, okay, over the rough surface? So it's rotating over a rough surface here, okay? So here, that will depend. This is the center here. This radius, okay, how much is this radius? And the angle of tangency here, theta. How much is the angle of tangency? Let's remove the hatching here so that you can see and focus on the important things, okay? So if I'm applying this force T2, okay, so T2 wants to move or pull the cable, okay, but it's not moving due to friction, so this is the direction of impending motion, okay? So this is the direction of impending motion. So that means that along the contact here between the cable or the belt, where's the contact? From here to here, there is a frictional force. What's the direction of the frictional force? Okay, it's perpendicular. You have a normal force perpendicular to the surface. As you see, the surface is not straight, okay? It's curved. So that means here, the frictional force is always tangential to this surface. This is the frictional force. Okay? You agree with this? Okay? So now, let's go ahead and try to understand the equilibrium here and find this relationship. We're just targeting this relationship. If we know how much is T2, how much is going to be T1? What do you think? Will it be larger than T2 or less than T1? T2.
T2 is larger.
Yeah, I'm applying T2, okay, but the frictional force will make T1 less than T2, okay? You're going to lose some force in this belt due to the friction, okay? So let's see how we're going to do this, okay? So how we're going to do this, we're just going to study, okay, as you see here, we have this curved surface. The cable gets tangential over here from this point of contact to this point of contact, okay? We're just going to study a very small, infinitesimal element on this curved part, okay? So I'm just going to take small part here, okay? ds, okay? What does ds means to you? It's so small, right? It's almost zero, right? That's what ds means, so small that it's almost zero. So I'm going to take this element, which is so small, almost zero, and study the equilibrium of it, okay? So let's study the equilibrium of only small infinitesimal segment of length ds. Okay? So let's try drawing this. Okay? Hopefully I will draw it in a nice way. So this is this segment ds, just enlarged, okay? ds. So on this ds, at the start here, there is a tangential force in the belt that is equal to T, okay? When you move a distance ds, there will be a force here, but this force will change, okay? Or actually, let's say, we said here T2 is larger than T1, so this one is going to be larger, right? So let's say that the change here is T plus some tension, additional tension, dt, okay? So it changed the magnitude of the tension along this small distance, ds, changed by the magnitude of dt, okay? Now, those angles, okay? Let's draw those angles here. This angle here of the change of along this segment ds, let's call this angle d theta, okay? Everything here is d, any change is d theta, okay? ds, why? Because it's so very small change, okay? Along very small distance. So again, the change in the angle theta is going to be so small, okay? So now, what we have from the start here to the end, since this is a very, very small length, okay? That's why we chose a very, very small length, ds, okay? We're going to assume that the curvature is negligible along this length, okay? So if the curvature is negligible, so this is the direction from the start to the end, okay? I can do this because this distance ds is so small, right? It's almost zero. So the direction of the curve is the same. I can assume definitely that the direction of the curve is the same as the direction of this black line, okay? So now, along the direction of this black line, okay, it's where the contact between the belt and the surface happens, right? So you're applying a tensile force here. So what will happen that the surface here will give you a normal force perpendicular to the surface, right? So there is an N here, right? It's applied on this small surface ds, so we're going to call it dn, small normal force along this surface, right? And now there is a frictional force along the tangential surface, okay? This is now represent like the direction of the surface, right? So the tangential force or the frictional force is in this direction. This is the direction of the impending force, right? So the tangential force is in this direction. So here we have df, okay? Small frictional force. If we're on the verge of equilibrium, then this df is mu s dn, okay? So now this small part is under equilibrium, under the effect of those four forces, T plus dt, dn, and df, which is mu s dn. So we want to study the equilibrium of it. How to study the equilibrium, right? The equations of equilibrium, which are the summation of the forces in the x direction equal to 0, the summation of the forces in the y direction equal to 0. So where's the direction of the, where's the x direction, where's the y direction? They don't have to be like this. X and y, okay? If I choose this is x and y, as you see here, you know, all the forces are, you know, inclined. I have to find the, you know, the angle theta for each of those forces and find the components, x and y components of each of those forces. So instead of using this coordinate system, this is the coordinate system that we're going to use here. Okay, the flag here. This is the coordinate system that we're going to use. Y and x along the direction of the small infinitesimal L. Okay? So that's y and x. Okay? So now, from some trig, if this angle is d theta between those directions, okay, this angle now is d theta divided by 2. Okay? So now, let's draw this in purple here. This angle is d theta divided by 2. And this angle here, between, is d theta divided by 2 as well. Okay? So now, okay, what I want to do is find the components of this force T along the y direction and along the x direction. This angle is d theta divided by 2, so this angle is d theta divided by 2. So what are the two components? The x component is how much? T.
T
Theta
cosine
sine
d theta over 2.
Cosine or sine?
of sine.
No. This angle is d theta divided by 2. This is t, this angle is d theta divided by 2. So it's cosine. Okay? Cosine the angle d theta divided by 2. And the y component is t sine d theta divided by 2. Okay? I want to do the same thing here. The two components. Here we have t plus dt. This angle is d theta divided by 2, so it's cosine d theta divided by 2. And here we have the force d plus dt multiplied by sine d theta divided by 2. Okay? As you see here, we have cosine d theta divided by 2, and we have sine d theta divided by 2, right? The angle d theta is very, 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 very small, right? It's almost equal to 0, right? It's a small angle, right? So, anyone has a calculator? You have a calculator here, right? Just do an experiment. What is the cosine of a small angle? Let's assume a very small angle. Let's here. Oh, everyone has a calculator. Just try this, okay? If you have a theta angle, okay, of let's say 0.001, okay? Let me know how much is cosine theta and how much is sine theta.
Sine theta is 0.999.
0. Point,
For the cosine,
the cosine is
0.999.
0.9999, right? Till the end, right? 0.999999.
Yeah. Sine is
So it's almost what? 1,
yeah, so
right? What about sine theta?
it's 1.74.
No. Sine theta?
0.0000.
0.00.
4.000.
9?
1.745.
It's theta is 0.001. So sine theta is 0.00?
0, 0.
No.
Okay.
I got 5 zeros on it too,
Yeah, it's,
for sine theta.
You have something wrong here.
I got 1.74 multiplied by 10 to the negative 5.
No, what will happen is sine theta actually will be so close to the angle theta itself. I don't know what you're doing here, okay? Just, okay, let's try smaller angle. 0.0001. Okay? How much is sine theta? You should get the same, sine theta that is almost this
No,
number.
we got 1.74
0.00.
multiplied by 10 to the negative 7.
Okay, so the thing is, look, if you try to plot theta, here you have sine theta and cosine, and theta versus theta. How does this curve look like? It starts from 0, it goes like this, right? This is pi over 2, right? So that the slope here is 45. Okay? That means when theta is so small, along here, when theta is about 0, theta is almost equal to sine theta. Okay? So when theta is so small, theta is equal to sine theta. Okay? So, and when theta is so small, also here, if you have this, you want to plot cosine theta versus theta, it goes like this. So at theta equal to 0, cosine theta is 1, and the slope here is almost horizontal, so it remains 1 for very small theta, okay, at the beginning. So for small angles, sine d theta divided by 2, it's a very small angle, is equal to the angle itself, d theta divided by 2. Okay? And cosine d theta divided by 2 is almost how much? 1. Okay? So let's start doing this now. Let me try to make this smaller. This was the x and the y. So now let's see the summation of the forces in the x direction. Okay? What are the forces in the x direction? We have those two components, those two purple components. We have those two forces, the normal force, the frictional force, and those two components. Okay? So the summation of the forces in the x direction. What are the forces in the x direction?
Negative 2 cosine
Log negative t cosine,
d theta over.
which is 1.
Yeah.
Okay? So negative t. Okay? What else do you have?
df, which is
Negative df, which is mu s dn.
positive
T plus TD.
Positive t plus dt. Cosine the angle, which is
1.
1. So those are equal to 0. You have negative t and you have t. Those cancels, right? So you have dt equal to mu s dn. Okay? Or moving dn to one side of the equation, so dn is dt divided by mu s. Okay? dt. That's the, divided by mu s. Okay? And then let's apply the other equation. So this is equation 1. What's the other equation? The summation of the forces in the y direction is equal to 0. What are the forces in the y direction? Negative t sine d theta divided by 2. What's sine d theta divided by 2?
D theta what?
D theta divided by 2. Okay? What else?
Positive, yeah,
Positive dn. What else?
negative t.
Negative t plus dt
That's multiplied by
multiplied by
D theta what?
d theta divided by 2. Those has to be 0. Right? So what do we have here? Let's see here. Negative t d theta divided by 2. Negative, those both were negative, negative t. Yeah, and negative t d theta divided by 2, so this becomes what? T d theta, negative t d theta, right? Plus dn, negative dt d theta divided by 2 has to be equal to 0, right? You agree with this? I just sum those two terms. So it became negative t d theta. Okay? Now, looking to this equation, we have t. It's a large number, right? A number, t, tension force. And then d theta, it's a small number, almost 0. dn, it's a small number. dt, the change in the tension, it's a very small number. d theta, it's a small number. What happens when you multiply a very small number by a very small number? It becomes smaller and smaller, right? So we're going to just say this is second order term. It's small number squared, okay? So we're going to assume that this is 0 because it's small number squared, right? So now we have dn equals to t d theta, right? That's equation 2. What do we have here? Equation 1, dn was dt divided by mu s, and from equation 2 we have dn equals to t d theta. So equating dn from both equations, we have t d theta equals to dt divided by mu s. Okay? So if you have an angle, change in the angle of d theta, the tensile force will change with this magnitude, dt. Okay? But actually, what we have here is we want to find the change in the tension along this angle theta, not along a very small angle d theta. So what would we do here? We're just going to integrate both sides of the equation. So we have here d theta mu s equals to dt divided by t, okay? Then by integration, I'm just going to integrate, okay? So integrating the angle theta from, let's say, from here to here, okay? So from 0 to this angle theta, okay? From 0 to the angle theta, and t is going to change from what to what? From t1 to t2, right? Here, along this angle theta, going the angle theta, the tensile force changed from t1 to t2. Yes?
We're integrating with the respective foot.
So here we have I'm integrating here, the right side here. With respect to d theta, I'm integrating this one with respect to dt. Okay? So now, mu s is constant. Integrating d theta. What's the integration of d theta?
US
Theta.
theta.
Okay? So we have mu s theta. What's the integration of dt, 1 over t dt? Hmm?
Derivative. Oh.
No, not 1. 1 over t. What's the integration of 1 over t? Hmm?
As a log of theta.
Yes.
I thought it was derivative.
So we have len t, okay? From t2 to t1. So it's len t2 divided by t1, right? So we want to find the relationship between t2 and t1. So let's take the e, the power of e. So here e power mu s theta is equal to e power len t2 divided by t1. E power len something is that something, t2 divided by t1. So therefore, the relationship between t2 and t1 is that t2 is equal to t1 multiplied by e to the power mu s theta. This is how the tensile force in the cable is going to change in an angle theta. So as the angle theta increases, the tensile force is going to change more. Okay? And mu s, the coefficient of friction of the surface, okay, of that surface. So this equation, you don't have to memorize it. I can give it to you on the test. There is no problem. Okay? So T2 is larger than T1. Okay? That's what we have here. And theta is in radian. Okay? This is an important remark. Okay? Theta has to be in radian. Any question here? Okay? So now let's go ahead and solve an example. So example 8.8, okay? We have here this system. Simply not go. Selecting. Select. I'm just going to leave it like this. Okay? And here this is allowed to rotate its surface. So this is smooth. And this surface is rough and rough surfaces. Okay? And then we have a cable here running like this. There is a force T, and it's running like this. Then it goes down here, okay? This angle here is 45 degrees, okay? And then there is a load here, okay? So, in this problem here, let's see what we're required to find. What are the given things, okay? So it says here that the maximum tension that can be developed in the shown chord is 500 newtons. Okay? It's the same chord. It goes like this. The maximum force that it can be in this chord is 500 newtons in any given segment. Okay? How many segments do we have? We have this part, and then here, here, here. Each part of those, the maximum force that it can hold is 500 newtons. Okay? It says here, if the pulley at A is a smooth surface free to rotate, and mu s for the fixed drums at B and C is 0.25. So this is B and this is C. Okay? We're required to find the mass here, this mass, okay, that we're talking about, to keep the chord in equilibrium. Okay? That's what we're looking for. So we are putting this mass here, and we're having a tensile force here. So if this mass becomes small, this tensile force will start, moving the chord up, moving this way. Okay. So what's the mass that we require to prevent this motion? Okay. So we're talking here about a frictional problem. Okay, on the verge of equilibrium. Okay. So in this problem, what's the direction of the motion, of the impending motion?
We're pulling from here, right? Or
Yeah. So this way. So the cable wants to move in this direction, right?
Yeah.
So let's copy this. So now, this is the direction of impending motion. So now, the question is, if this is the direction of the impending motion, where's the largest tensile force? Where's the largest tensile force? If this is T, the force here will be lower or larger than T?
Lower.
No, it's not the same, because this is a rough surface. So what will happen? You will lose some tension here, right?
Yeah.
So this is going to be less than T. This is smooth surface. So if you have some force here, how much is this force here? It's the same.
Yeah.
And then here, you have a force here. And then it goes around this flat surface. What happens? You're going to lose some force. So this inside force is going to be less than this. Okay?
Yeah.
So the maximum inside force is in which part? Here. Right? So how much is the maximum inside force can be?
500?
500 is given. 500 newtons. The maximum force here. So T is 500.
Yeah.
So we start with 500, we go around this drum, it becomes less than 500, we go this way, it remains 500, and then here it becomes less, the force that becomes here becomes less and less, and it's, in equilibrium under the effect of this load. It's provided by this mass. So we want to find how much is this mass, so at the end the force here is 500. Okay? So let's start part by part. Studying the drum at B. Okay? This is the drum at B. You have the force here, T, which has to be 500 newtons, right? 500 newtons. And then you have the force here. So this T, you want to call it T2, right?
Yeah.
The larger one, and this one is T1, right? So now, this goes from here, okay, to this angle. So how much is theta?
So 180. So what?
90 plus 45.
90 plus 45, okay? So this is 90 plus 45 degrees. This 90, okay, plus then 45, okay? So it's 135 degrees. This is in degrees, okay? We want this in radians. We want the angle in radians. So how to represent 135 in radians? Do you know how to represent an angle in radians or not?
Multiply by 180?
No, divide by 180
Divide 180, yeah.
and multiply by
By.
pi.
Yeah.
Pi is 180, okay? So here this is equal to 135 divided by 180 and multiplied by pi, which is 3 pi divided by 4. Okay? So now, what we have here, the equation that we had, T2 is equal to T1 e power mu s theta. That's the equation that we had, that we derived. The relationship between the two forces. Okay? So just applying this equation here. T2 is 500 newtons. It's equal to T1, I don't know how much is T1, multiplied by E, right? Power mu. How much is mu? 0.25 multiplied by theta. How much is theta? 3 pi divided by 4. So therefore from this equation I can find the force T1. Okay? So T1 is 277.4 newtons. Okay? And then you have here the pulley at A, okay? Smooth. So studying the smooth pulley at A, this is the smooth pulley at A, you have T1, which is 277.4 newtons. It remains the same, T1 277.4 newtons. So remains the tensile force, or the force in the cable, remains the same. The force in the cable remains the same. And then we're going to study the last one. The drum at C. So for the drum at C, you have the cable coming this way. How much is this tensile force? 277.4 Newton, right?
Yeah.
And then it goes vertically like this. We want to find this force T.
Again, T1.
Okay, but now we're calling this one T1, so don't get confused, right? You have to, the equation says T2, right? Equals to T1 e power mu s theta, which is the larger one.
But T1 is going to be less than,
277.4, yes, right?
that's going to
Equals to that tensile force. So here, I'm just going to write it T1 equals to T multiplied by,
T2. Oh.
this is T1 and this is T.
Oh.
Let's call it T3.
Okay.
Okay?
T1 is going to be bigger than T.
Yeah, you just need to know which one. So here we have T3 e power mu s. Mu s is 0.25 theta. So what's theta from this center here? The angle of tangency.
That'll be the same.
Same.
This theta, which is 3 pi divided by 4. Okay? So 3 pi divided by 4. So therefore, T3 is equal to
154.
153.9 newtons. Now you have this weight. You have T3 and you have the weight of the object, W. So how much is the weight? It's the same magnitude. W is equal to T3, so the weight is 153.9 newtons.
Divided by gravity.
Right?
That's about 9.1.
So this weight is equal to mg. Right? So therefore the mass is 153.9 newtons divided by g, which is 9.81 meter per second square. So that means that the mass is 15.7 kilograms. Okay? That's the required mass to prevent the motion. Okay? If the mass is less than this, okay, then the cable is just going to move. Okay? Any question here? Okay, great. So now we finished chapter 8. Okay? Let's start chapter 9. Okay? So new or in this journal document and chapter 9.
Are we going to have a quiz today? Are we going to have a quiz today?
Why? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Right now there is 9 students, and there is 2 who left, so there was 11. Actually, now the number of students is 14 in this class. So, you want to have a quiz? You're gonna do well. Are you gonna do well on the quiz? You keep asking for a quiz. You just give me the impression that you just, get the full mark on that quiz. You just want to punish them. You don't like that guy who was sitting beside you, right? Once he left, let's take a quiz.
Let's do it.
Okay, so now we're going to start chapter 9. It's an easy chapter. We already, discussed something in chapter 9 before, okay? It's about the centroid, okay? So just a reminder, do you remember when we said if you have a uniform load or a distributed load force like this, okay? It's P of X, okay? So how to find the magnitude of this load, okay? So the magnitude F here, the resultant force. Do you remember this? FR.
Yeah.
We said the resultant force is just the integration of P of X dx, right?
Yeah.
And then the location here,
X equal
X bar,
Integration of px x dx.
X dx
P of
dx
X,
over dx dx.
X dx, divided by the integration of P of X dx, right?
Yeah.
This location, okay, is the centroid, okay, of that load, okay, or the center of gravity. Let's call it like this. So let's apply this same concept here, okay? The force here, we have a distributed force that looks like, okay? So we're going to apply the same concept now, okay? So apply. You see, he didn't leave. He just came back, okay? You still want to take a quiz? So apply the same concept of the equivalent force of a distributed force to find the weight of an object. So now, let's say we have an object that looks like this. It's an irregular shape, okay? So we want to find the weight, okay, of that object. So the weight is distributed here along the area, right? So let's say here you have small area, it has some weight. Here you have a large area, so this part here has a larger weight, right? You agree with this? Okay? So to find the weight of this object, I'm just going to divide it into small parts, okay? Let's say each one has an area of dA, okay? Small segments. And we're just going to find the area of each of those segments, okay? And from that we can find, the weight of the entire body. So instead of writing dA here, I'm just going to write it dW, the weight of each of those segments. Okay? So the weight of each segment is not the same. It depends on the weight of it, right? So for the shown irregular object, to find the weight of the object, we're going to divide it into a set of, again, infinitesimal elements, each of weight dw. So each segment has a weight dw. There are different, each segment has a different weight from another one, okay, from the other one. So now, if you want to find the weight of the entire object, what do you do for those segments? You just add them on, right? So the weight is just the addition, the summation of those dw. But if dw is so small, it's not summation then. It's what? Integration, okay? So you integrate the weight of each of those segments. The weight of each of those segments is function of its area, right? As its area increases, okay, so dw is function of the area of the segment dA, okay? So you just find dA of each of those, and then you do the integration, okay, you're going to find dW, right? You do the integration, you find the weight W. So now, the weight, I can know the weight from the integration of dW. But where is that weight applied? So the point at which this load or weight is applied, okay, is called the centroid, or to be more precise, it's the center of gravity. Okay, we're going to call it the center of gravity. So this is the x, the y axes, okay? Now the location at which W is applied is called the center of gravity. Sometimes I prefer calling it CG, but sometimes it's just given the notation G, okay? Point G is the center of gravity, or CG, you can use whatever you want. I was raised up using the notation CG, but like for example, the textbook prefers the notation G, okay? But no problem, it's a notation, use whatever you want, okay? So where's that point, okay? Where's that point? So those are forces, right? The weight of each segment is a force, right? So let's take moment here about this line, O, okay? Let's say this is the origin here. So this is the x-axis, this is the y-axis, okay? So now, we want to find this distance, x bar. So taking moment about the y-axis, taking moment of what? Two equivalent systems, the small infinitesimal elements and the equivalent load, okay? What's the moment of each of those infinitesimal elements? It's this dw multiplied by its distance x, right? So it's the x dw, and then you sum them up, right? This is equivalent to the moment of this force, which is w multiplied by x bar. So this is equal to x bar multiplied by w, right? That means that x bar is equal to the integration of x dw multiplied by w, and w was what? The integration of dw. It's the same as we did earlier for the load, right? The distributed load. So this is the location of the centroid, x bar. So this is the location where this load w would be applied, okay? The weight of the object. This is the center of gravity. This is the point. So what does the center of gravity mean? If you have an object that looks like this, I guess this looks like a potato maybe, okay? and you want to hold it in your hand, okay? I want to just put it on a point and it doesn't rotate. Where is that point? The center of gravity, okay? This is the point, okay, where you just put this potato on, okay, it's not going to rotate. Any other point, okay, it will just rotate, okay, due to the, you know, the moment of this weight about the center of gravity, okay? So now this is X bar, okay? What if I just, you see here this potato, okay? I'm putting it like this. What if I flip it 90 degrees? Okay? Now the weight is in what direction if I flip it by 90 degrees? Instead of being in this direction, when I flip it, it's going to be in this direction, right?
Horizontal.
Right? Horizontal. I flip it. Okay? So if I flip this object, if the object was flipped by 90 degrees, the centroid now, or the center of gravity, is at a distance y bar. Okay? So if I rotate it, it's the same W, but it's in this direction, right? So where is that point? Okay? We're talking now about this distance, y bar. Where is this distance, y bar? So again, you're going to do the same, but now you're going to divide the segment, or the body, the object, into segments parallel to the x-axis and take moment about the x-axis. So what's the moment of this? It's this dw multiplied by y, right? So we're going to divide the object into small segments parallel to the x-axis. Axis, and take moment about the x-axis. So therefore, we have dw multiplied by y, and the summation of those is equal to y bar multiplied by w. So therefore, y bar is equal to the integration of y dw multiplied by, divided by dw. So that's the location of the centroid. Okay? So now that point is the centroid, x bar and y bar, the intersection of the 2 points here, x bar and y bar. That's the centroid, or the CG, the center of gravity, CG. Okay? So it has like 2 directions, okay? 2 coordinates, x and y, x bar and y bar, okay? That's the center of gravity of an object. This is the point then, okay? Where when you hold it, it's not a line now. It's a point where you hold it, it's not going to rotate, okay? So this is, as you see, it's the same formula, but one for the x bar is the integration of x dw divided by integration of dw, y bar is the same, but it's y instead.
It's just
Right?
different respect to the rest of it, integrating with respect to x and respect to y.
Exactly, okay? What if you have a 3D object? for a 3D object. The potato is a 3D object here. It's not an area like this. Okay, what we have here, we're just having a slice, right? For a 3D object, okay, there is a point, the CG, the center of gravity, okay? So you have to find this point in space, okay? So where's that point? X bar is the integration of x dw divided by the integration of dw. Y bar is the integration of y dw divided by the integration of dw. And z bar is the integration of z dw divided by the integration of dw. That's the center of gravity of the 3D object. Okay, this is how you can find it. Okay, you have to divide it into slices in all three directions. Okay, each time you find the x, the y, the z coordinate of those. Okay, if you do this integration on the using the weight, we call this the center of gravity. If you do the integration using the area, we call this the centroid. Okay? So they are similar to each other. If you use a homogeneous object with the same rho, the same density, then it's the same. The center of gravity is the centroid. There is no difference. Okay? So here, I'm just going to answer your question. Just give me a moment. If we use the area instead, we get the centroid. So the centroid, again, x bar, it's the same formula, there is nothing different, but it's x dA divided by the summation of dA. Y bar is y dA divided by the integration. If we're talking about an area, okay, then it's dA. For a 3D object, it's not area, it's volume then, okay? X bar is the integration of x dV divided by the integration of dV, volume now. Y dV divided by the integration of dV, and Z bar is the integration of Z dV divided by the integration of dV. And that's it for today. So what's your question?
We got it.
Huh?
I was just going to ask you to say what you had said again, but you wrote it down. So okay.
About the volume?
Yeah.
Yeah, okay. So any question? Okay, so see you on Monday. So today